we'll get started with our third session for today as I mentioned, on sensing and AI. Everything from field deployed sensors to how AI-driven computing can process that data. And first up, our first speaker is Nathan Kutz, who is in both ECE and applied math here at UW, and he is also currently the director of the NSF AI Institute for Dynamical Systems. Nathan's work has been recognized by many different awards and recognitions, and so without further ado, take it away.
Thanks so much. Hey, great to see everybody. What a beautiful day in Seattle, yeah? Days like this, you kind of go like, it's pretty nice being in Seattle. Anyway, I would love to have my office right there. I'd be happy to share it with any of you, because it'd just be right there. So I'm going to talk. I just made up this title. I was telling Mars back here, I was like, when did you come up with this title? And it was like 5 minutes ago. I decided to put for just about everything here, because really what I'm going to tell you about is this architecture that's actually based on really sound mathematical underpinnings, which I won't have time to share with you, except for very basic ideas from a first course in differential equations. Not just the first course in differential equations, the first day of that course. So a lot of the stuff here I learned when I was 20 years old. And that was a class that made me want to be a professional applied mathematician, which I like to think I am. Sometimes I doubt that, because I just too much I don't know. But we're going to do sensing. We're going to do model reduction. We're going to learn physics, and this can even be used for data simulation, signal processing. It's a very generic architecture. And at least I'm going to start it off, how it started off was sort of as a sensing paradigm. So the idea here is to think about spatial temporal data. It doesn't have to be spatial data. It could be any kind of high-dimensional state space. It could be a collection of neurons. In fact, we are a place we are applying it to. But here, this is just a representation of some dynamic systems, the chemical reactor, where the red dots represent 3 measurement locations, where I take the time history in, I just listen with those sensors, and then I put it through this architecture, which is a shallow recurrent decoder. So the current part is a time pipe there. So those sensor measurements come into the time piece, which is a sequence of measurements. So this is a sequence model in machine learning. It can be an LSTM, it can be a gated recurrent unit, it can be just a generic RNN, it can be a transformer network. I don't really care. We can trade them all out. In fact, we've done all that. Trade out the time pipe for whatever your favorite time pipe is. From the latent space of that time pipe, you decode it back to the full state space. You can do it with a simple shallow decoder. You can do it with a UNet. Pick whatever you like. Doesn't matter. Mix and match. Okay? All right, but mostly what this is a product of time and space. And when I was 20 and I took that first PDE course, that was the major technique you had for solving PDEs, was separation of variables. You just write it as a product of time and space. Okay? And this is also the majority of our numerical methods for solving PDEs. Write it as a product of time and space. March forward in time. Okay? And so this is kind of a generalization of this concept into this here. And then so what we're going to do is apply this, but we're going to do a lot more than sensing. So first of all, it started off as a sensor problem here with Jan Williams, who is now in his 3rd year. He actually started working with me on this before he came to grad school. He was an undergrad. And we started this collaboration at Carleton, and then I recruited him here to the UW, where he's doing his PhD. So what we are looking at here, for instance, is you're over here monitoring at these 3 points, randomly picked. You don't even have to care about the sensor location. It's agnostic. As long as the sensor is participating in the physics itself, you just put them wherever you want. Now, I'm going to tell you how important this is later, because I spent 15 years working on optimized sensor placements. Okay? So when I tell you about this, I'm undercutting all that 15 years of work. So it's like I have a vested interest to tell you about how you should place your sensors and how to optimize for that, because I did a lot of work on that, and now I'm saying, don't worry about it at all. Put them where it's convenient for you. And then you run these through, And here's your pipe, and then you decode. And I'm showing this actually on isotropic turbulence. And the reason I can show it to you on isotropic turbulence because it actually works. So this is a mapping. And by the way, turbulence is usually the hardest thing to do. At least in the spatial temporal data sets we look at. If you can kind of do something like turbulent flows, it's really pretty impressive. Because a lot of methods don't work on that multi-scale of a data set. This does a great job with it. And here are the main ingredients of why this works. One is the separation of variables. Two, if you don't know this one, let me tell you about it. It's a mathematical result from 1981 called Tockin's embedding theorem. And like a lot of great mathematics, it was an interesting result that nobody cared about. Right? Oh, that's kind of interesting. It's totally useless. Right? So I live in that math world. And the thing is, you don't know things are useless until they're useful. Okay? And this is one of those tools. So what Tockin's embedding theorem says is if I have a dynamical system where all these components are coupled together, if I take one of them, and if I look at the time delay embedding of that, it tells me about all the others. And the way it's written is it's diffeomorphic to the actual thing that you were trying to measure, which means there's a continuous transformation that's differentiable. The problem with Tockin's embedding theorem in 1981 is nobody told you how to get it. So for almost 50 years, we've not been able to actually exploit this theorem. But now what we have here is this architecture, and we have training data sets. So instead of this thing being diffeomorphic, it's one-to-one. So once I get the training data set, I can map it, I have it, and I can just listen to a time delay embedded version of a signal and tell you about all the measured, unmeasured variables of that system. The other thing important about this is a decoding only strategy. I'm not encoding to a space and decoding, which requires me to create inverse pairs. One thing you don't do in computational science, if you can avoid it, is compute an inverse. MATLAB, for a long time, so you could just, there's an age gap here. People below a certain age don't know what MATLAB is, and people above a certain age, I grew up on that. So MATLAB, if you try to say inv A, it would say, warning, do not do this, okay? It's not very often that these commands tell you that, like you're doing something dumb, right? They're usually like, okay, it's your business if you want to do it. This actually would warn you. We've known this since the 60s. Here, by having a decoding-only strategy, there's no inverse pairs. So all of a sudden, it's going to completely change the game for us in terms of how quickly it's going to work, how robustly it's going to work. Okay, so let me just show you an example here. This is a data set from the WELL, which is a data set that's benchmark data set that's out there. And sort of, it's basically shallow water dynamics on a 2D flow all around the spherical domain. So we're going to use this now we're going to use it for sensing, but to build reduced models. So there it is. There's the dynamics. I'm going to listen to 3 locations, take the time series data, run it through my time pipe, decode it back out to the full state space. Okay? Now, this can still be expensive because this is very high-dimensional data, right? It's a grid on the planet Earth as a proxy for it, let's say. Now, if you just saw the other talks here, so NOAA does this stuff, and they're trying to get 5-kilometer resolution, which all of a sudden makes this thing super massive. So why don't we do the following? Because, by the way, here's how this got motivated. Here's one thing I don't know how to do. Okay? So my grad students all know how to put code on GPUs. And I don't really know how to do that. So I'm like, I'm going to have to do a GPU. So instead, I came up with this idea. Instead, take all the data, do an SVD, look at a low-rank subspace, do this again, but train now on the SVD of the data. In other words, you've encoded it into a lower dimensional space. So you can take these massive data sets. You just say, look, here's an approximate low-dimensional embedding. Train on the coefficients of that. This, all of a sudden, I'm training back on my laptop. Everything you're going to see here, you can just train on a laptop because I can do it in compressive training. So massive data sets, we can just shrink down. I don't need a GPU. I can just do it on a laptop. Okay, granted, my laptop has 96 gigs it's got a big memory. But I paid a bunch of money for my laptop. So it's no ordinary laptop. But still, you know what I'm pointing, is like I'm still doing training here, and I'm doing essentially minutes of training to get models like this. So let me just show you how it works. So here is the data, and let me just show you this here. In fact, not only can I just train compressively, by the way, those are the 3 points there that you see. I can also have one moving sensor. So what I can do instead is take, how about instead of 3 sensors, 1 sensor. And you see that, I don't know if you can see the sensor moving around there, but you, actually, I think you see it in the next one here. You see the sensor moving around? I tell it where the sensor is, I do the time recording, and I can reconstruct the entire dynamics by listening to one time series measurement of that sensor as it moves in time. Why? Because of Tawkin's embedding theorem. It's not magic, it's math, okay? Arthur C. Clarke, he has that any sufficiently advanced technology is indistinguishable from magic, and so any sufficiently advanced mathematics, which is a proxy for technology, same thing. But this is how it works. Not only that, on the bottom picture, instead of training on my SVD modes, I just train on spherical harmonics, because that's the natural basis for this. So what I have here is a super lightweight reduced order model that I can basically just listen to one single sensor around the globe, or 3 fixed, and I can just tell you what's going on everywhere else. Okay? We did this on some more data here. Here's a real video of flow physics. And again, this is from a benchmark data set. You see the yellow dots there? Those are the sensors. We took the time series of those sensors, and here's the actual video, and this is just the reconstruction of that from listening to those 3 measurement locations. And by the way, this was done parametrically. So we had a set of videos where they changed the conditions of the video, the flow rate, the properties of that cylinder. And so this is a withheld data set, a withheld video. We listen to these 3 locations, do the reconstruction. Okay, and it has both symmetric and asymmetric behavior with that. The other thing, okay, so this is for model reduction, sensing to mapping and model reductions. Mars, who's back here, whose poster was right out there if you ended up talking to him, we decided, hey, let's go ahead and go play around with the latent space, because the latent space is where all the magic is happening. So we go into the latent space, and now what we do in the latent space is tell it to learn a dynamical system. So say, go in here, try to pinch the dimension of the latent space down as small as you can, and learn the dynamical systems. And the way we do that is what's called sparse identification of nonlinear dynamics. It's a method that Steve Brunton and myself came up with here at UW a while ago. And so you can also learn a linear model, but here's what you get out of this system. This is sea surface temperature data, weekly data. And so you take these weekly snapshots, you run it through 3 locations. You see the sensor locations. You take those in, and this is sort of doing a reconstruction, but we're not using it for reconstruction now. We're learning a remodel, and here's the model. What it learns for you is a 3x3 linear ODE, which you can give as a homework set in a differential equations course. That, in fact, all the students should get right. Because it's linear, constant coefficient, super easy. And the ones that don't get this right, you get a little concerned with. You say, hey, are you doing okay in class? You should work harder on your homework. This is not like, okay, I just expect the smart kids to get it. This is, anybody can solve this one. And by the way, these are glued to these 3 modes down here. And so now you can do these rollouts. Here's a 100-week rollout from the data. And one of the things you miss is you do miss some of the finer features, but remember, we're only sampling every week on this. Okay. So again, video, model. Here it is. This is the model you learn. You just go straight from video. Here is the latent space nonlinear dynamics of that video. So all of a sudden you can solve this, and by the way, this thing has a fixed point, has a limit cycle. We can roll this out to infinity. If you don't like a nonlinear model, build a linear one, 6x6. Now I can just roll this video out as far as I want in the future. Okay? So these are the kind of things we can do in this latent space. So, final example here is turbulence. Check this out. So here's data, and I went back to turbulence because turbulence is hard. But what's interesting about this, in this model when you roll it out, 16x16 linear ODE, there's the solution to it. So when I roll this forward in the latent space, it's saying to you, look, I can solve this. I need 16 dimensions. I want to roll this forward. In fact, if they come in complex conjugate pairs, so it's really 8 modes. 8 modes oscillating together that creates this turbulent data set. And we normally think of turbulence as the hardest thing. Very high dimensionals, and what it's saying is that I can approximate this pretty nicely for you. And it can do a really nice rollout and preserve a lot of the high spatial frequencies. Has an interesting thing here, which is convex landscape, globally convex landscape. And this is why we don't have to even hyperparameter tune. The other thing, even if it trains fast, if you've trained a neural network, typically what you're in for is just not fun, because you have to hyperparameter tune a neural network. So normally, because of this decoding architecture and because of this, these same problems on videos, when we first started doing this with an encoder or decoder, it took us 6 to 9 months of hyperparameter tuning to make it work. And then if you breathed on it wrong, it wouldn't work. Here, one afternoon. Still works, okay? But the other one didn't. So we're pretty impressed with that. So what are we going to do with this? So I'm going to hurry through this, but what we did is we're going to shred for nuclear reactor digital twins. We talked about nuclear reactors earlier today, and it is secretly growing. Like, nobody wants to talk about nuclear power, right? It's still sort of a dirty word, right? On the other hand, it's pretty clear that the energy budget, especially in Europe, they're thinking about this a lot, because Putin might say, hey, cut off your oil. You know what I mean? It's complex landscape of politics, but certainly France and Italy have quite a bit invested in making these things safe. Well, how do you make them safe? Well, you need better physics models, for one, for sure. You need to be able to understand your physics. It's hard to make a safe device when you don't really know how it operates. Here's the crazy thing. You go look at this device, you start thinking about all the complex engineering, multi-scale, multi-physics, a zero failure environment. And what we have to do modeling of this is we have forward models that have been built over generations, and this is just sort of the workflow of this multi-scale physics engine. And really what it comes down to is 20-coupled PDEs. So even if you don't care about nuclear physics, this is kind of the state of the art. 20-coupled PDEs, and then you ask them the following question. Okay, you have these 20-coupled PDEs. How'd you verify this was okay? All right, well, it's right. It's like, well, so you ask them, well, can you measure in that 20 PDEs? We can measure one of the fields at point locations. So even if you were to build this, your pathway to making this is almost impossible. You have a reality, and then you have a model that you can't even test. And so what we did with this is start giving a pathway towards this, is trying to make the digital twin of this, which is to start looking at this reactor. One thing that you can do is you can actually, first of all, you can't place sensors where you want. The only place they can go is on the side, and you can only measure like one of the fields, temperature. Maybe you can get a velocity measurement, but you got 20 fields to measure. But here, I told you about Dawkins' embedding theorem. I don't have to measure the velocity. If I give me the time history of the temperature and it's connected, I can tell you what's going on with the velocity. We do this all with the proxy method. Okay? So here it is. Here's the device. This is it in practice. We put the sensors on the edge of the device. That's the only practical thing to do. You can't put a sensor in the middle of that thing. It'll melt. And you start doing the reconstruction and state space estimation. And so this is kind of our pathway forward, is we actually have this working in the system. It doesn't care about positions, which means we can put it in convenient places for us. You can basically tell you what's happening with unobserved fields, and you can build ensemble models, so then it allows you to do uncertainty quantification as well, which is really important for safety considerations. And these are really big scale simulations, by the way, right? So I like working with people who spend the time doing this, because this is hard simulation effort that they have available to them. And here's the whole nuclear reactor device. And what you're looking on the left is the actual full order modeling physics, and on the right is the shred model with 3 temperature measurements on the side. And you basically nail it. Okay? Here's just a side view of that. Who cares? Okay. Anyway, I'm just going to leave here on this picture. Part of this is sort of starting to help us really build much better models for devices like this that really need more efforts in part because if this is going to be a viable pathway forward, if we're going to really invest in nuclear, which I don't know if we have a choice, frankly, but and I think what we just need to figure out is how to build safe devices, do design engineering. We need a pathway like this where we have a template which allows us to now interrogate the real machine, make predictions about what would actually be there and compare them to our simulations and start closing the gap from sim to reality. And this is the pathway forward, at least one of them that can be there, because this is your nuclear digital twin, and you can even set up the shred architecture to be in data simulation mode to do that. So I'll stop there. Thanks.
All right, thanks so much. Do we have any questions? I see one from...
I can go. Cool. If it doesn't matter where you measure, it doesn't matter how long you measure?
Good question. So typically here, we found a lot of, so essentially these measurements, you have a time history, and we listen to about, 40 delta T's in the past. I think that's our default setting. So whatever you measure, you just listen to the last 40 delta T's, and then you train on that, and you get all the fields out. It's really, it's kind of remarkable. But again, when you look at the Dawkins embedding theorem that's been there almost 50 years, it's staring you in the face. It's been there for 50 years. And it's like, oh, that's all I'm doing here. So all this architecture is, if you want to think about it, is a Dawkins embedding, generalization of Dawkins embedding theorem. And so, in some sense, the more you think about it, the more it's like, of course this has to work. At least that's what it's been for me. The more I get into the theory of this, it's like, yeah, of course this works. It is obvious that it works. We've known this should work. Separation of variables goes back to the time of Fourier, right? That's that one. Not doing matrix inversions, 1960s, Dawkins 81. So everything I'm talking about here is concepts that have been 5 decades or more around and well established, and that's all that got put together to make this.
Well, I think, oh, do we have another question?
Quick question. How do you could run this model if you have discrete events that are separated by different forcing mechanisms and boundary conditions, and the next event may be coming with totally different situation? So in that case, how many events would you need to be sampling?
Well, great question. There's two things. One is if you do have forcings and events, there is a version it's working on which has the control aspect to it. So you would start learning a model that learns how the actuation or how you're changing the system is affecting it. But in general, this is always a big problem, right? With you've got to be able to have a fairly rich training data set. If you want to predict this event that you've never seen, you're not going to generically do it unless you have enough data that has seen many of the things you're trying to actually predict. Even though we don't use a lot of data here, right? In fact, you can almost train on the fly. It's so fast. So there is that. You could always upgrade the model, but the actuation part of this, where you actually bring in the control element, will make a big difference, I think.
Thank you.